So if you're peeking at homework really fast and trying to see, why is homework so long? Oh, that's not, is that you guys? Hold on. Yes, this is you guys. This is not you guys. Let's get out of there. Okay. So plotting points in homework, that's going to be the beginning, all the way up until, all of those are super easy and fast. Cool. Starting in the 20s and 30s, okay, what's going on there? You're taking a polar point and making it rectangular. You're taking an r theta and making it x, y. Huh. I think this coordinate conversion page might be helpful, right? Coordinate conversion page. To go from polar to rectangular. That's this whole next section of homework. The next section, from rectangular to polar. Go from x's, y's. Oh, wait, use a graphing utility to find? You can use your calculator? Make sure you have your calculator. After that, then we go rectangular to polar. Oh, hey, that's this example. Then we use our calculator some more. Have your calculator. Then, all the way down here in the 70s, it starts to get a little hard. Wait, all the way down in the 70s. Uh-oh, how much homework do we have past the 70s? Oh, not too bad. Wow, we're still complaining. So then we have some conversions of rectangular polar with equations, polar rectangular equations, and now all of a sudden we're still in polar rectangular equation conversions, and we're done with homework. Maybe I'll take away the Ferris wheel problem just to be nice. Okay, so maybe I'll take away the Ferris wheel problem just to be nice. You're welcome. Bloop, 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 bloop. You're welcome. Are we done complaining now? Okay. So, as I go to Google Classroom to change that up, you guys, we need to see if you guys can even plot the points, because if that's supposed to be the easy part of homework, we better review it. So, easy part of homework, plotting points. Yesterday, where did point A end up and why? Where did point A end up and why? You're at the North Pole. You're at the pole. How do you go to 345? Angle of 45 from wherever the 0 is. Someone would have to point you in the 0 direction. That's 0. Okay. Or you have like a little protractor around your feet. Anyway, go to 45 and you walk out 3. What? 3 miles? Sure. 3 feet? Sure. 3 inches? I don't know. But you walk out 3. That's A. But where did B end up? The opposite way. Did anybody hear my really quick illustration to help you remember that yesterday? Yeah, kind of. If you have a positive relationship to someone, you see them in the hallway, you'll be like, oh, buddy, right? And go towards them. If you see someone, maybe Mr. Huff, and your skirt's a little like, guys, you don't do that. But anyway, maybe you'd be like, I'm backing away, right? So positive, you go towards, and negative, you go the other direction. Does that kind of make sense in a real life, or at least a polar application? So what if I was to give you a few more points? Ready? I want you to graph point C and point D and point E on your own, and let's see if you end up in the right spots. You can use the exact same graph that you were starting to build yesterday. Wait, but we didn't do all the angles. But can't you just take an angle and like make it when you need it instead of showing them all? We didn't do all the radii. Well, can't you kind of just make the radii that you need when you need it? You don't have to have this humongous, complicated graph to graph these points. So let me give you a few things. Like, what if I was to give you something, let's do 2, 150. Let's do negative 5, 220. Let's not do that. Let's do negative 5, 270. And then let's do 315. Nope, that's wrong. I'm putting an angle in the R spot. 315 degrees. Ready, set, go. Can you try to graph C and D and E? You're like, well, I didn't show all of them. Well, that's okay. Make the second quadrant, make the third quadrant, make the fourth quadrant, but don't do all the circles. Just wait until you have an angle, and then if you have that angle, approximate where he is. And then see if you can figure out about where the point will go, even without having the huge, complicated graph. Maybe a little bit, but so far we haven't done any sine, cosine, tangent, but could be useful to know where angles are, like where they show up. No, that's what I mean, sorry. You want to know where 150 is. And you're like, oh, that's 180 minus 30. But you also want to know when they give you radians where that is. So looking at the unit circle angles and where they land would be a good idea. Yeah, counting by sixths, fourths, thirds, halves. I'm just doing degrees right now to make it easy. But if you guys, when you guys see radians in homework, you're going to want to go back to your unit circle or remind yourselves that there's actually a way to convert between radians and degrees, right? So if worst comes to worst and you're totally terrified, I guess you could always remember if you're given a radian, you can always multiply by 180 over pi, get the degree and think of it that way. Oh, sorry, I was taking away that nasty word problem in your homework in Google Classroom. I forgot. You don't want me to forget that one, do you? This is homework number 70, yeah? Nope, 65. Just kidding. Number 127 is, oh, nope, oh, that's not it. Officially erased. Save. Oh, you're going to miss out on the Ferris wheel problem. Everybody groan, make me feel better. Never mind, no one do anything. All right, so, boop. Question. Point C. What quadrant? Yeah. On what angle line? 150. This guy. And out how many radii? Wait, out towards or out away? Towards. Got him? Cool. Did you have to like draw the entire second quadrant to get there? No, not really. Just needed the 150 line and needed to go out 2. How did you go out 2? Did you guys think about like the whole circular connection between the tick marks? I didn't show you tick marks, but couldn't you do tick marks on the 180 also? Does that make sense? You can do tick marks on him too. You can even do that axis like you would a normal XY. You can do the exact same thing on 270 also, and you can do tick marks if you can keep it straight. Sorry, mine's a little crooked. And you can still think about the circular even though you only have an X and Y. Lauren? Kind of. Because in this one, 150 and polar positive R's are just headed to an angle. So you can have R's going in the left direction. But you can also have negative R's going in the left direction when it's away from a certain angle. So it's more the towards and away. So you're just thinking about the angles individually. So 150, yay, 150, positive, oh, go the other way. So it's not so much right is positive, left is negative, up is positive, down is negative. That whole thing has been like blown up. Cool. Letter D, point D. What quadrant? It's not a quadrant, but where is it?
It's on an axis.
It's up. Do you see it? It's not a quadrant. It's up. Why? Because where's 270?
It's the down thing, but it goes the opposite
But I'm not,
way.
yeah, I'm not going towards 270. I'm going the other way, right? I'm backing up. I'm 1, 2, 3, 4, 5. Imagine you're on the pole. Turn towards 270. And then you're like backing away. Maybe there's a bear the other direction, right? A polar bear. Hey, I brought it back. Where's point E? Oh, 315. Okay, he's in the fourth quadrant. Whew, so it's going towards 315 or away from 315. Wait, are you going anywhere? It's at the pole. Yeah, it's at the pole. It didn't go anywhere. Wait a minute. So what would be another point at the pole? Joe, are you taking notes? Thank you. I don't want to take off points of your notes next time. 0, 0. That would be at the pole. Anything that? A 0 anything. Because you might have turned, but if it's 0, are you going anywhere? No, you're staying on the pole. So wait a minute. Hold on. This just made things a lot more complicated. So how many ways could you still be at the pole? infinitely many as long as r is 0. Oh. How many ways could you be at position A? Can someone give me another point that would also land in the exact same position as A? Another, oh, well, that's interesting. Another way of getting to A. What's another way that I could have asked you to get to A? Ooh, -3, 225. That's good. You could have been backing away from the 225 angle. Yeah. What's another way?
405.
Wait, how did Joe get 405? Not the freeway. Only one person cracked a smile. Anyway, 3, 405. He just went around. Why? Because you go all the way around, be back at 45, and then walk out 3? Could you go all the way around and land on 225 and then go backwards 3? Could you spin around 5 times and then go out to 45? Could you spin around 5 times and then go back from 225? Co-terminal angles. How many co-terminal angles are there? So how many ways can you describe one position on a polar graph? Ruh-roh. But don't worry, we're not going to try to spin you a million times like Spirit Day games. Okay, let's go back to our triangle. Did anybody figure out anything that they could label from the triangle yesterday? R, yeah, who's R? Just thinking the right triangle, who's R? Yeah, good. R is directed distance with polar, but just think geometry. Hypotenuse, thanks. R is the hypotenuse. Boop. Just think the geometry of it. What else can you label from the triangle yesterday? The X. Think about geometry. What part would that be? Not hypotenuse, but adjacent. Focus. Opposite. Who's the opposite? Y. Who's the angle? Theta. And who's this guy? The pole. Okay. That's the triangle we saw yesterday, true? Now, we haven't been going x's, y's. We've been going r thetas. But then we just talked about how there are infinitely many r's thetas that will match up with the same point. Now, they have to be related. And on that 45-3 app, it'd have to be some coterminal of 45 or some coterminal of his 180 away going backward. They have to be related in a very different polar points to get have the XY way, because the XY way, there's only one way to get there. Go over, go up. You're done. Oh, that was so close. Didn't even try it. Anyway, come back. Maybe I'll try that some other day. So r theta, you can spin and spin and spin. XY, you go straight there. So it can be helpful. Remember, you're supposed to have your calculator out because there's a whole calculator section. But let's say they give you r theta. And you can usually tell that because right here it looks like an angle. Maybe it's like a pi over 4, or maybe it's a 135 degrees. Every now and then they give you something awkward like 1.7. You're like, I don't know who that is, but the directions say from polar to rectangular. Either way, if they give you an r theta, well, how do I get to, can I just give you some cool formulas to use, and it's basically all out of the right triangle. Is that okay? So here's some cool triangles to use. If you're given r theta for converting points, you can point, Lauren. Now it might be helpful not just to review your unit circle for where the angles are, but also who is cosine at, who is sine at for plugging in. But this is when you're going from a polar point to a rectangular point, and then you should be able to say from those formulas, oh, so that's my x and that's my y. Wait, just to practice that. Yes. But there's also a whole section of homework to go the other way. And then there's 2 sections that say how to use your graphing calculator to do the work. So what if you're given x, y, and you want to get to r theta? Get from r theta to x, y is actually pretty easy. There's only one x, y point that could even possibly be an answer, so you're done. Once you plug in, as long as you've done it correctly, you're done. It's no big deal. Nothing to worry about. This one, can I just say it's a little bit trickier. This one's a little bit trickier. This one's a little bit trickier. But let me show you the formulas first. The R is actually super easy because the R says, aren't I, or isn't he, the hypotenuse? So can't we just do x squared plus y squared and then square root both sides? Wait. But if you square root a squared, it does cancel out, but couldn't it be plus or minus? And didn't we see r's that are sometimes positive? I'm going towards, or negative, I'm backing away, right? So r could technically be positive or negative. I think I'm going to have to be thinking about pictures. We don't just need r, we also need theta come from y if we use tangent, opposite adjacent. Right? We've seen this formula kind of in vectors before. Now here's the struggle. In this one, when I say, yay, r theta, I don't actually mean, yay, automatically, you're good, use it, r theta. What I mean instead is combine plus or minus r's with variations, what, of theta to land on an appropriate r theta. That just got complicated. Maybe. Didn't I just ask you a second ago, like, what some different ways of landing on the same point would be? And it was like, oh, we'll go way and then go backwards, or go around and then to that angle and then go out, or go around and then to the other angle and back. Or maybe we could even go the negative direction. You'll have the information you need when square rooting x squared plus y squared. You're going to have to think of them as puzzle pieces that can be varied, like the positive r or the negative r going towards or going away, the theta, maybe adding 360 or adding 180 to make a proper point that lands in the proper place. And the key to the trickiness, I would say, is before any of this work, draw a picture. Because what you need to figure out is what quadrant this original point is. Maybe he's in the first quadrant, so he's really easy to think about, but maybe he's in the third quadrant or the fourth quadrant or the second quadrant, and your natural plugging and chugging to the formula won't land you there, so you have to use a variation. It's not that big a deal. If you're in art and you don't have what you want, you start mixing other colors to get what you want, right? In math, if you don't have exactly what you want right away, use the pieces that you're going to find to get to where you need to go. Calculator's out. We're going to do it by hand first. And then we're going to see what the calculator can do as far as helping us. But by hand first. Lauren, go ahead. Let me see. Appropriate. Sorry. A-P-P-R-O-P, and then I was getting lazy. An appropriate, I guess I should be proper. So we'll do this. We'll say find all this. Bloop, bloop. And then combine the plus or minus r's with variations of theta to land on an appropriate point r theta. You have to make sure that whatever this is lands on the same place as that. The nice thing with this guy is he's super easy. There's only one x, one y that'll get there. You're good. But this guy, okay. So I have two different points. Can you guys tell which one's polar? The one with an angle and the direction stay polar. So then I guess that means that one's rectangular. I'm trying to make it so you guys can see the formulas with the points, but I know it makes it hard because of the lighting and the new, they're messing with my projector and everything's a little bit different. But the top one is a polar point. We're trying to get to an xy, a rectangular. The bottom one is a rectangular point. We're trying to get to a polar, an r theta. So just to keep you honest, to keep you going in the right direction, there's an r theta. Trying to get to, our answer should be an xy. And this one is an xy. Trying to get to an r theta. And which one right now should I put a star by? And that he's going to be your one for sure. The second one. So let's start with the easy one. Okay. If that's my r and that's my theta, how do I find my x? Got it. For y, it's going to be r with the sign, yeah. Uh-oh, we're going to have to know the unit. Oh, yeah, I already told you guys that. The unit circle says 11 pi over 6 is going to have a cosine of root 3 over 2 and a sine of negative 1/2. So negative 3 times cosine. 1, 2, 3. That's sine, which is why I'm going to plug in 1/2, but negative because it's in the fourth quadrant. 3, 2, 1, 1, ding, 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 ding. Oh, nope. I'm at pi over 6. I'm sorry. 1, 2, 3, 3, ding, 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 ding. Why do I keep going to pi over 3? Man. 1, okay, haha. 1/2, but negative fourth quadrant. 3, that's cosine, root 3 over 2, positive fourth quadrant. I know it's not gorgeous, I know it's not pretty, but we don't have to get the decimals. It's okay for us to go ahead and just steal it and say, hey, it's negative 3 root 3 over 2 and positive 3/2. Now, if you want, you can double check both point conversions. That way you double check. You could double check both point conversions. That way you always make sure you land in the proper place. What quadrant would a negative x and a positive y, I think you guys caught up by now. What quadrant would a negative x and a positive y land in? Wait, second quadrant, but I drew. Oh, that's not my point. That was my unit circle, right? That was my 11 pi over 6, so be careful. If you draw pictures of unit circles, you might get confused. We never drew our picture for this guy. 11 pi over 6 is down here, but why would the point have not been down here? I'm backing away. So second quadrant, are we good? Yeah, we're good. We would have gone 11 pi over 6. Which does have things like a cosine of root 3 over 2 and a sine of negative 1/2, which was helpful in plugging in. But the point isn't towards 11 pi over 6. This guy has a negative relationship with him. It's the other way. So second quadrant, match, we're good. But how would you convert this dude down here? Okay, what formulas do we have? R squared equals, yeah, x, take them, square them, plus y, take them, square them. Oh, and then if we want to get r, we're going to square root, right? Okay, so hold on. Doesn't the square root squared cancel? And a negative times a negative is a positive. And then square root squared cancels. Kind of. I'm just doing that for a second. I get square root of 6. But why am I going to put an r with a plus or minus? Absolute value of r says positive or negative, could be either. Is Jason in A-push? No, he's just gone today. I have my r, but my r could be, well, remember, it could either be going towards angles or away from angles, whatever I need. Wait, what point or what quadrant does this guy go in? I might not know exactly his number. Second quadrant. And some of you might be like, oh, wait, it's over and up the same amount. I think that's like a 45, 45. Anyway. Keep going and say, well, I know how to find theta. I'm going to do theta equals tangent of y. Now, it's the same thing as tangent inverse of -1, and some of you are like, ah! Square root of 3 over 3, 1 square root of 3. 1 is a number I can deal with, haha. But some of you, especially when you hear you can use your calculator on Monday, are going to be like, ding, 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 I'm going to put it in my calculator. So if you ding, 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 put it in your calculator, or if you remember that it's a pi over 4, well, what happens when you do put it in your calculator? If you're in degree mode, it's going to give you negative 45. And if you're not in degree mode, it's going to give you a negative decimal equivalent or approximation for pi over 4. But here's my question. Where's that angle? So how can I take the idea of I'm allowed to go toward any angle I want, and I have the angle right now of negative 45 degrees or negative pi over 4. How can I make a point that would link? I could go the negative way. I could go negative pi over 4 or negative 45. Can I go towards the angle? No, I need to go. So I'm going to use negative root 6. Is that a valid polar point? Yes. Could you give me another one? Someone else might have gotten there a different way. How could they have gotten there? Yeah, maybe they would have gone this direction instead and said, okay, well, if this is negative pi over 4, I want to go this way. What would this angle be if you went the other direction from him? Yeah, so they could have gone 3 pi over 4, and all of a sudden you're allowed to have a positive relationship with him, so positive root 6. If you wanted to be really nasty and mean, you could start doing coterminal angles. Please don't. And I have to figure out whether or not you're right. But those are at least a couple different polar points. Now, I did say there was a way to use your calculator to do some of this work. So, because our homework does say, use a graphing utility to find, use a graphing utility to find, which I might have assigned you tons in there, or I might not have, it's still something useful for us to find. So, bloop, bloop, let me get out of there. How do we use, let me get to where the light is better. Where's the light better? There he is. Okay. How do we use our calculator in order to convert these points? Now let's just go ahead and use the examples, if you guys don't mind, that we just did. The examples we just did were negative 3, 11 pi over 6, trying to get to, oh no, we're going to have to figure out his decimals. It's okay, we'll see if it works or not. And then we transformed this guy, and I would have just written 1 point, but we ended up actually finding a couple. So here we go. I want you guys to go ahead and go under, I have to remember where it's at. Nope. There it is. What are the things that we were given? We were given radians, yep. That's sad. We should go to radian mode. Because the first angle was radian. So, mode, oh, I'm already in radian. Got it. Do you guys see this nifty little second apps angle thing where we used to go get the degrees and the minutes? Remember him? Second apps? Do you see something like R to P and R to P and P to R and P to R? Why would they have two? Rectangular point to polar R, radius, and rectangular point to polar and then polar point to rectangular X and polar point to rectangular. Now in some ways it may be even harder than doing it just the formula way, but let's see if we can figure this out. The first point that we had was polar and we were going to rectangular, so we would be using these two options. So polar point to rectangular X. What was our polar point? We had negative 3, comma, right above the 7, right? 11 pi over 6, and we're in radian mode, right? I am. Double check you are. I'm giving the polar point saying, please go get me the rectangular X. Oh, that's gross. It's nasty. It's disgusting. Oh, so was mine. Negative 3 rad 3 over 2. Let's see if it matches. Dun, dun, dun. Dun, dun. Yeah. Oh, second caret. Yeah, second caret. Now, if I want to go the other way, well, I'm going to have to go back in that angle menu and go down to polar to Rx Ry this time. I can steal the exact same point, or write the exact same point, because I'm doing the exact same conversion. All it's doing, guys, literally in the programming is plugging into r cosine theta and r sine theta. That's literally all it's doing. So it doesn't really seem that exciting. 3 halves, 1.5 is exactly what I got. But if we were doing the other way, we would just go ahead and say, okay, now I have a rectangular point to a polar radius. I wonder which one they'll choose, because didn't we say there are infinitely many combinations and a calculator can only give one answer? Which one are they going to choose? Positive. Interesting. And I'm guessing that's going to be a square root of 6. It is. They chose a positive r, not a negative. So then maybe they're doing this other variation? Let's see if they get it right or if they get it wrong, because they have to change that angle. So I'm going to go ahead and go to the angle menu, rectangular to theta. Let's see if they get it right. So negative, rad 3. I'm sure the programmer was smart enough to talk about if the first is negative or if the second is negative, but... Oh, is it off? Oh, calculator screen. Lo siento. Plugged in my... Let's see if this is truly 3 pi over 4, which is not just simply tangent inverse of. Oh, they're good. They're really good. Computer programmer thought through all the different options and told the calculator, if you're in a negative x positive y, you better add pi to whatever tangent inverse is. But our brains can do that just as well as long as we consider the picture, where it should be, and take all of our clues to make it appropriately there. Any questions about the calculator function? Where do I find all those cool little things? Second, apps. Yeah. My distracted ones. Well, it doesn't matter like function, parametric, all that stuff, but it will matter the radians as to what answers they give you. So they would have given you 135 instead of 3 pi over 4 if you had been in degrees. Does that make sense? Yeah. And then it would have been totally off for 11 pi over 6, sadly, if you were in degrees. Okay, that's point conversions. That gets us all the way in homework to the 70s. How do we get the rest of the way? Well, we need one more page. Wait, there's not one more page. There's just problems. Exactly. You guys ready? That right triangle that I just showed you gives you everything you need to know for finishing homework as well. That right triangle I just gave you gives you everything you need to know for converting. We just went point. You can do it too to equation conversions. These ones are rectangular to polar. How would I know, even if I couldn't read the gray? Because there are x's and y's. That's rectangular. To polar, I need r's and thetas. This page, I have r's and thetas. I'm going from polar to rectangular. I need x's and y's. So on each of these, I'm going to draw the triangle, because to be honest, I think he's the key to all of this. X, y, r, theta. X, y, r. Because we've worked with this guy all year, the right triangle, in so many different ways, so many different applications. I have x equals 10. I can even draw a picture of x equals 10, a vertical line at 10, but how on earth do I get out x, take out x? Oh, substitute. Well, to substitute, I need a formula. Formula. Well, guys, what formula would put x and r and theta all together, adjacent and hypotenuse and angle? Isn't that cosine of theta equals x over r? Couldn't I multiply both sides by r? Oh, that's a formula that you just wrote down. X equals r cosine theta. Can't we just plug that in? R cosine theta equals 10. Guess what? You're right, but the book's going to have something like r equals 10 secant theta. What? Because they divide the cosine to the other side, because in your polar mode, wasn't it r equals in your y? The proper form is to get r by itself like we get y by itself. So technically, dividing by cosine would be 10 over cosine. Okay. So we had that. All we had to do was go look for it. How about the next one, though? Is there an xy formula? No. But there is a way to get x and to get y, isn't there? So maybe there's no xy formula, but there is a formula for x and a formula for y. X would be r cosine theta. Y would be r sine theta. Couldn't I say r times r is r squared? So 2r squared cosine theta sine theta equals 1. That's right! But it's not very proper because r is not by itself. It's right, but it's not very proper because r is by itself. So let's see if you guys can figure out why they could have put the square root of 1/2 secant cosecant as another variation. What?
Oh, divide by 2 first, and then move it.
Divide by 2, 1/2. Divide by cosine, 1 over cosine is secant. Divide by sine, 1 over sine is cosecant, and square root. And to be honest, guys, some of these, it's so nasty, they don't even do the square root. Like, some of them might just be like, get r as alone as possible. Like, sometimes they would just, and I think they do, just leave it r squared because of what Joe was about to ask. He was like, how did you know positive? Couldn't it be plus or minus? So sometimes they might just leave it r squared because they're like, yeah, plus or minus square root, that's messy, we'll just stop. So sometimes they just stop with r squared to make life a little bit easier. So, okay, hold on. Looking at the triangle, we can kind of pull out formulas and plug in. Even looking at the formulas we just wrote down a second ago. But what about this? Sometimes, if worst comes to worst, you might actually even want to draw a picture and be like 2 pi over 3. If that's the, wait. There's no r's, it's just theta. Yeah, it's the theta line. It's a line! Shouldn't we be able to do a little bit and not even use the triangle and say, because it goes through the pole, so I can say plus 0, and all I need is slope. Oh my goodness, how do I slope from an angle? Section 10.1. M equals tangent theta, the incline. Oh, I could just cheat a little bit and do tangent of 2 pi over 3 times x, and I could actually do that on my own. Wait, what's the other way this could have, or you could have gotten here? You could have actually said, I don't have a formula for theta, but I do have a formula for tangent theta. The other way of getting here is that instead of drawing the picture and seeing that it was a line and figuring it out from there with inclination, you could have actually said, but hold on, I know tangent of theta is y over x. So you could have taken tangent of both sides, saying, I know x is tangent. Square root of 3 over 3, 1 square root of 3. So square root of 3 in the second quadrant, y equals, if you plug that in, negative root 3 times x. One's with a picture, one's with, I know tangent. Okay, take tangent of both sides and then plug in. Now I'm just giving you a warning, somewhere around the 100s, which is pretty close to the end of your homework. But this is one of probably the hardest types of problems. You might come across not just cosine of theta, not just sine of theta, but cosine of 2 theta. Remember how we talked about formula quizzes the other day? And we referred back to that really long formula quiz. And there was a double angle formula for cosine. And one of those double angle formulas for cosine is cosine squared minus sine squared. Or 1 minus 2 sine squared. Cosine squared minus 1. Pythagorean theorem. R squared plus R squared. We still need to get rid of this thing. How do we get rid of that? Well, I need to know who cosine is and square them. I need to know who sine is and square them. But guys, I don't have formulas this time. I have a triangle. Who's cosine of theta in the triangle? Adjacent over. Oh, wait a minute. I still have r's when I plug in. Maybe I shouldn't have gotten rid of my r. Maybe I should wait. Maybe I shouldn't have gotten rid of my r. Sometimes, like, it's really gone. There are more. So I can have x squared over r squared minus y squared over r squared. Wait, aren't these common denominators? X squared minus y squared all over r squared. How do I get rid of the r squared? I'm almost there. X squared minus y squared equals r to the fourth, or r squared squared. Didn't we just say r squared is x squared plus y squared? Get y by itself? Sometimes it's so messy, they just leave it and they say, x's and y's, we're done. Yeah. Sometimes it would just be way too hard to get the y by itself. Kind of like on the page before, I left it r squared. It looks like 2 over r. Sorry, that's messy. Sometimes it's like, you know what? You went from r's and thetas to x's and y's. Good job, gold star. Let's stop. There's a good job. Way to go. Gold star. There you go. Let's stop. So where does that bring us? 2B. End of homework. Taking out the Ferris wheel problem. That was number 109. Bloop, 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 bloop. That's weird. Like 109 is at the end of this section over here. And not all of them, guys. The cosine 2 thetas, like those are the nasty ones, or the sine 2 thetas. You have to go back to like old formulas to try to get those. Number 109 would have been the worst. Did I not even do 109? He would have been nasty because he was 3 theta. Oh, I called that 109. I didn't do 109 because he was even worse than the one I did. Anyway, I actually did 108. Which is your homework problem. Get out of here. I'm being too nice. Bye. Later, guys. I will